Hello everyone. Uh, we have discussed Bernoulli's equation, which was lecture 20 uploaded on YouTube channel. And then after that, we discussed creeping flow equations. So these were two limits. These were two limits of Reynolds number. So I hope you can see my screen. So one limit was yeah. So Reynolds number approaching infinity, and the other limit was Reynolds number approaching zero. This Reynolds number infinity, what does that mean? Reynolds number, if we write, that is rho VL by mu. Rho is density, fluid density. V is some velocity scale. L is some length scale of the flow. And mu is the viscosity of the fluid if it is constant. If it is constant, then mu is some characteristic viscosity. Similarly, density also, it is a characteristic density of the flow. Now, what does it mean by Reynolds number approaching infinity? It means that either viscosity approaches zero, or velocity, length scale, or density approaches infinity. Okay, or a very large value. So we also called these kind of fluids as inviscid flows. Inviscid means non-viscous, which don't have a viscosity, which have zero viscosity essentially. So inviscid fluids are also known as ideal fluids, which have zero viscosity. In reality, there are no such fluids. So this may be a approximation that we can use. And Bernoulli equation, we derived Bernoulli equation. This came out after we substituted viscous stresses to be zero, and we wrote Navier-Stokes equations along a streamline. Okay, so Bernoulli equation is valid along a streamline, and this was P plus rho v square by 2 plus rho gz equal to 0, equal to some constant c along a streamline. So if we know that there is a streamline, we can say that pressure plus the second term, which is also known as dynamic pressure, and the third term, uh, a sum of all these is constant along this streamline. Okay, this is what we saw for inviscid flows. So Bernoulli equation, while deriving this, we also assume that the flow is steady. Apart from being inviscid, it is also steady. There are a few more assumptions here. So while deriving this equation, so you can go back to that video. That was lecture 20. And the other limit that we saw in the next lecture, lecture 21, was Reynolds number approaching zero limit. What does that mean? It means that either velocity goes to zero, length scale is very small, density is very small, or viscosity is very, very large. So that may happen for highly viscous fluids. We can approximate a flow of a highly viscous fluid that is flowing very slowly to this limit. So that was creeping flow limit. Okay, so here we have not derived anything like a Bernoulli equation along a streamline. We just derived the Navier-Stokes equation for creeping flow. We also derived um, dimensionless governing equation for creeping flow. So what it looks like is del P is equal to mu del square U. Okay, or you can change, this is not dimensionless, there shouldn't be a mu here. Okay, so this is what it looks like. And the Reynolds number term that we took to one side, and we put Reynolds number equal to 0 while deriving this equation, so that all the acceleration terms, the time term, as well as u dot del u term, that goes to 0. Okay, so that was creeping flow. Now in today's class, what we'll do is we'll take some problems on Bernoulli equation, and you can solve those problems. Okay. So let me just define a few terms first of all. As I said, P here is called pressure, but what pressure is this? This is also known as static pressure. This rho v square by 2 is known as dynamic pressure. Okay, and this is also known as, this is also a kind of pressure. We can call this gravity head. Okay, or pressure corresponding to gravity. So although the name is static pressure, it does not mean that everything is static here. Things may be moving. There is a flow, of course, if there is a velocity here, but still you can have this this P. We can define this P. Just a second. Yeah. Okay. And a sum of the static and dynamic contributions, this is known as the total pressure, or there is a special name for this. This is known as stagnation pressure. Okay. So now what these are physically, that we can see in an example. There is a device known as pitot tube, which is used to measure wind velocity on an airplane or any other moving object. So on an airplane, you will find several small devices. protruding from the wing or from the tail of the aircraft. So those are used to measure the outside velocity. So that will give you what is the velocity of the airplane itself, because the air is stationary. So that measures the relative velocity. What it looks like is something like this. And then, okay. So this is a tube. You can imagine that this is a tube. This is a conical section at the front, and there is a central hole in this tube, and there are holes on the periphery. Okay, these are holes on the entire circumference here. Okay, and then so now you have two chambers here. One is this chamber one, where the air can flow. So the outside air that is coming something like this will enter the first hole here. Okay, so this will be filled with this air one, and the second chamber is this central region where there will be the second air. And now you can connect these two so that you have this one, and then there is a third liquid filled in here. This is mercury or something else. These days we don't use this mercury. What we have is a diaphragm here, and it is measured electronically. So there is a pressure sensor which is electronic. It is not a liquid like this, but just to illustrate the pressure difference, I am showing this. So here you have a difference of heights between these two columns. So let's call it delta H. Now what happens is at the tip here, when the air hits this tip, it doesn't actually enter. The velocity goes to almost zero. You can try this. You can have a sheet of paper and make a hole in it, make a small hole in it, and let the fan blow the air, or whatever you have at home, a fan or a cooler or anything like that. Let it hit one side of the paper and see what velocity you get, what velocity you feel on the other side of the paper. So just behind the hole, you'll see that the velocity goes to zero, almost zero. If the hole is very small, it will go to almost zero. So that is known as stagnation pressure. So the wind here, it has some velocity. So some component is dynamic, and there is some static component, P plus rho v square by 2. P is the atmospheric pressure, almost 10 to the power 5 Pascal, and rho v square by 2. V is the speed of the airplane. So that is the pressure that you will feel at this point, at the tip. So that pressure is transmitted in this tube. So that pressure is seen by this limb. So this is P plus rho v square by 2. It is known as stagnation pressure because all the energy of the fluid is converted to energy here. The fluid here comes to a rest as it hits this hole. It is not moving anymore. So all the energy has been converted to purely pressure energy, purely static pressure, or it is known as stagnation pressure in this case. And the hole here, if you see, actually the air does not enter this hole like this. I'm just showing it to show you that uh, this is the same air as what is flowing outside. So the air actually flows like this outside that hole which is on the circumference of this tube. So this hole here, it feels the pressure, it feels only the static pressure component. It does not restrict the flow, it does not obstruct the flow. So this dynamic pressure is not converted to the pressure that this hole feels here. The air that comes in goes out with the same velocity. So this part is not changed. Okay. It is only this isotropic pressure P that is felt by this hole. We have already seen that this static pressure P is felt uniformly. Okay, we have already seen that if you have an element like this in a static fluid, the pressure on all sides will be the same on this element. So whatever pressure a particle feels here will be felt by this particle also. So it means that the pressure that is felt on this limb here is just P. And you know delta H. So you can say that whatever the density of mercury here is, rho Hg times delta H times G. That is the pressure difference between these two limbs. This should be equal to the pressure on one side of the limb minus the pressure on the other side. Okay, for it to be in equilibrium. So it is P plus rho V square by 2. Here rho is the density of air minus P. So that gives you just rho V square by 2. And here rho is density of air. So by rearranging this, you can get this velocity. Delta H square root. Okay. So this device is known as a pitot tube. Is this clear to everybody?
Sir,
Yes.
so if at point 1 the velocity is 0, then why are we taking P plus rho V square by 2 in limb 1?
This is about limb 2. We are talking about 2. See this
Yes,
green
sir,
color.
in limb 2. Yes, sir, in limb 2, why are we taking P plus rho V square by 2?
Okay. So if you apply Bernoulli's equation along this streamline at, let's call it point A, and let us call the second point B. Okay. Let us apply Bernoulli's equation, which is this P plus rho V square by 2 plus rho Gz equal to constant. Now rho Gz component will cancel out from both the sides because it is the same height. P plus rho V square by 2 at A will be P at A plus rho VA square by 2. This is equal to, we are saying that at point B velocity becomes 0. So there is only PB there. So pressure at B is PA plus rho VA square by 2. and that is what we want. We want the velocity of the airplane that is far away. What is the velocity of air far away from the pitot tube, right? So that's what we
Yes,
have
sir.
taken. Yeah.
Yes, sir. Thank you, sir.
Okay. Yeah, this I should have explained. This I assumed to be true. Okay, is there any other question? All right. So now we'll go to some problems. Mm, okay. These are again from Fox. Container. This height of the centroid is this tube is 1 meter, and this is 8 meter. This tube is open from here and from here. Okay. This height is not given. Only this much information is given. Also the density and everything is given. So assume it to be water. Uh, Now, first of all, let's say the initial condition is that the water is filled everywhere in the tube. This is the initial condition. There is no air in the tube, water is filled everywhere. What will happen to the water? Will it flow out or will it go into the tank? Or half of the water will go out and half of the water will go into the tank and the tube will be filled with air. So these are the three options. What will happen to this? Can you write here? And you can also do this experiment easily at home. You just need a tube like this, put some drinking water in a cup and suck the water in from one side until the tube is filled with water. Okay. Then remove your mouth from there and see what happens. Yeah. Okay. So many of you have written it will flow out. Yes, so that is the correct answer. It will actually keep flowing out. You don't have to apply any force. You don't have to suck it again. It will keep flowing out until this portion is dipped in water and the other end is lower than the first end of the tube. The water will continue to flow out. Some people also use it to siphon out petrol or diesel from tanks. Okay. You don't require any pump, just the gravity does its job and the water keeps coming out. Although the water has to climb here, but because there is more water on this side, it pulls the other side. Because there is no air gap in between, the pressure difference keeps pumping the water out of the tank. Okay. So now again we are using Bernoulli's equation for this, and real fluids don't exactly follow Bernoulli's equation because Bernoulli's equation is for steady flow. Uh, Friction is neglected, so inviscid flow uh, and incompressible flow and so on. But still, some qualitative results you can get even for real fluids. For example, this is water. So the problem is, what is the speed of water flowing out from this end if the entire thing is filled with water, and let's say it reaches a steady state? What is the speed, and what is the pressure at the highest point A of the siphon? So this is what you need to find. Also assume that the tank surface area is very big as compared to the cross-sectional area of this tube. So using this assumption, find out these two things: pressure at the highest point and velocity at the exit. And write the answer here. first answer is here. Yeah. So the velocity is fine. Okay, fine. Some of you have solved this. Here you can apply Bernoulli's equation between the surface of the water. So inside the tube, because we have to apply it along a streamline. So at this level inside the tube to the exit of the tube. Between these 2 points, if you apply Bernoulli equation, then you will get the velocity as well as pressure. So first you will get velocity at 2. Then to get pressure, you have to apply it between the first point and point A. And because of continuity equation, velocity will remain the same in the entire tube. So velocity at the end point at the exit will be the velocity at point A as well. Okay, yeah. So 11.7 is the correct answer. Okay, now let me give another problem. So now this problem that I'm going to give, this is an unsolved problem in chapter 6 of Fox book. This is problem number 6.10. So you are given that this fluid is incompressible, it is inviscid, frictionless, the flow is steady, the velocity field is given. ax I cap minus ay j cap, and it is given that there is gravity, and gravity is acting in the z direction, negative z direction. So positive z is that direction. Let me just, this is the negative z direction, and the magnitude is g. And these are, everything is in meters. The pressure is given at xyz equal to 0, 0, 0. That is the origin of the coordinate system. The pressure is P naught at 0, 0, 0. What you have to find is pressure at any point in this field, in this flow field. So please find this. This is inviscid incompressible steady state. Okay, first of all, can you write here what approach you are following? So are you trying to solve Bernoulli equation? Can you please write yes or no? Okay. Hmm. Okay. So Bernoulli equation is valid only along a streamline. If pressure at origin is given, then pressure at any other point along a particular streamline can be found out using Bernoulli equation. So for this given velocity field, um, For any other streamline using this pressure, it may not give you the pressure at any other point. Okay, because if the other point lies on some other streamline, then Bernoulli equation won't be able to give you that. But there are certain conditions under which that constant on the right hand side of Bernoulli equation is same even for different streamlines. So if you know that condition, then only you can apply Bernoulli equation for this problem, because here you want pressure at every other point, not just along one single streamline passing through the origin. So for this problem, it is better if you solve the entire Navier-Stokes equation or the Euler equation after making the assumption that the viscous terms are zero. Is it clear? Is there any question?
So,
Yes.
please repeat.
Okay. So I was saying that Bernoulli's equation can be applied only along a streamline. Here in this problem, you are given P naught at origin. So only those streamlines which pass through the origin, for them you can apply Bernoulli equation here. And that will give you pressure at XYZ lying only at on this streamline. So for any other point, for example, which lies outside this particular streamline, you will not be able to get the pressure Pxyz if you apply Bernoulli equation in this problem. Is that clear?
Yes, sir.
Okay. So at this point, it is P naught that is given. So the solution that I suggested, the approach is that don't use Bernoulli equation, use the Euler equations, which you get after simplifying Navier-Stokes equation, after assuming that viscous stresses are zero, or that mu del square V term is zero. So if you directly solve Navier-Stokes, then you will get this pressure. Okay, let me solve this. Let me write the Navier-Stokes first. This is the Navier-Stokes equations, and there is continuity also, del dot V equal to 0. First, let us check if continuity is being satisfied, if the problem is correct or not. So if you put here dou u by dou x, that is this component, plus dou v by dou y, this is the left hand side, del dot v. So here you get a minus a, that is equal to 0. So this condition is satisfied. Now we can proceed to the next part. So now we know that the flow is incompressible because del dot v is 0. Now we can use this equation, and we can neglect mu del square v because it is given that this is an inviscid flow. Also, because velocity does not contain any time term, so we'll neglect that also, the time derivative term. Now there is v dot del. What will be v dot del? Ax, let me write it, minus ay j cap dot product, okay, this whole thing acting on v, which is ax I cap minus ay j cap, which we'll write. This is equal to minus del p, and rho g. G vector is in k direction, rho g k cap. We can write this. Now this implies, now let us take the dot product of these two. We get ax dou by dou x minus ay dou by dou y acting on the velocity field ax I cap ay j cap del p. Also we can expand, but we'll wait for the next step. Ax dou by dou x acting on that velocity field. So let us take component wise. Ax I cap, so let us take the I component. I cap ax, that becomes a square x, dou by dou x of x is 1, then dou by dou y of x will be 0, so only this term will remain here. Then j cap ax dou by dou x of ay will be 0, ay dou by dou y of ay, both are negative, so it will become positive, and this will be a square y. This is equal to dou p by dou x I cap dou y j cap minus rho g k cap. And there is dou p by dou z k cap also, because that is the entire gradient of pressure. Now in k direction, the left hand side is 0. So dou p by dou z can be equated with rho g. That will be the equation for k direction. So let me write this in one corner. Minus rho g. So pressure will be equal to minus rho gz plus some function of x and y. Now if we put z equal to 0 here, we'll get f of xy equal to p naught. Right, at z equal to 0, because at x, y, z equal to 0, this is p, this is, okay, let us write like this. Then if we put x, y, z 0, we get p naught equal to f of 0 comma 0. Okay, later on we will see what this function f of xy is. Now let us write it for I and j directions. Okay, now you can integrate them, and from here you will get pressure, this function of x, plus some function of y and z, and from here x and z. Now all three of these have to be same because all are pressures, so you can equate them and find f, g and h. We have three equations, three unknowns, and this can be found. So we'll end here, it is already 11:57. If there is any question, you can ask now or in the next class. Okay, if there are no questions, we'll end here. Thank you.